Okay, hello everyone. Today we are proceeding with a lection on our discipline theory of signal processing. And I would like to start with a method that is called discrete cosine transform. This method will be also present in your practical task after you will finish with a spectral transform of Walsh and Hadamard that are the subject of the practical task number 3 that is already in our Google Classroom. Now I'm going to share my screen to show you everything that is necessary for our today work. So at first, let's have a look for our Google Classroom. So here you can see that there is a task, practical task number 3, that is devoted to the spectral transform of Walsh and Hadamard. All the instructions are in the file attached, and we detailedly considered this theory during our last meeting. So I hope you will not have any difficulties in executing this practical task, but if you will have, please address me in any time. I'm in contact and I'm ready to help you to understand everything that is needed. So I'm waiting for your uploaded works on task number 3, and the next practical task number 4 will be devoted to the discrete cosine transform. Actually, we already started considering this material in our presentation number 4 that is already uploaded by to Google Classroom. So let me to open it on the slide number 14, where the material that is devoted to discrete cosine transform is placed. Okay. Discrete cosine transform, or the acronym DCT. What does it mean? A couple words before. It's quite effective for the compression of data. And the compression, it's a very popular task that is that could appear in different applications where there are a lot of data that should be processed, and also to minimize, it is necessary to minimize the volume of the memory to store this data and to store the result of processing and so on. It's quite simple in calculation, at least in comparison with the classical Fourier transforms that we considered with you together already. Also, it is convenient that it could be represented in algorithmic form, so it's very good described in analytical form. And the next very important advantage of this method is that it operates only with the real numbers. So there is no complex numbers like in Fourier transform. That is one of the main disadvantages of Fourier. And actually, this method, discrete cosine transform, this is a method like that has a source of the Fourier itself. So it was created initially from the Fourier series, actually from discrete Fourier transform, of course, because now we are dealing with the discrete method. So if we will take discrete Fourier transform, DFT, and just take not all basic function, but only cosine component of it, we will obtain discrete cosine transform. So the idea is very, very simple. And because cosine components are real, and also there are an even function, like a pair function, we considered this issue before. So it could be considered as a basis for the new method. And actually it was, and it is used effectively and successfully in different applications. I will show it this application later. Okay, so let's go to the main equations of this method. There is a mistake here. We have a discrete Fourier transform, or shortly DFT, in a form like here in a red rectangular frame. And here there is a complex character of basic function. You can see it, you can observe it as a level of exponents, as an argument of exponents. We have this j here, that is the complex unity. And if we will divide, it's like any complex number could be divided into real parts and imaginary parts. And so if you will divide the basic function of DFT, discrete Fourier transform, and then take away only cosine component without imaginary part, only real part, so we will obtain something like here in the bottom of the slide, also in a red rectangular frame. So here we have a spectrum of discrete cosine transform. It is indicated like X in with the lower index C, that means cosine. And here is the real part of the Fourier spectrum that is written down above. And under the sum, instead exponent like it was in discrete Fourier transform, we have only cosine function with the same argument, k to b n over n capital, where k is like a counter that takes values from 0 till n capital minus 1. And I remind you that n capital, this is a number of discrete digits in original functions that should be analyzed, that we are taking to do something with, like original function. So we can put consequently these different values of k, 0, 1, 2, and so on till n minus 1, put it here, and obtained a different components of the discrete cosine transform spectrum. I will show it how it works, but before we have to consider different modifications of this method because it exists in different modification. The most common form of discrete cosine transform is here you can see it is a upper formula. X from k, and under the sum we have x from n, this is original function, and x from k is a spectrum, and the original function we are multiplying by cosine function with this argument k to bn plus kp over 2n capital. It is also could be presented like here. It's very simple transformation, like a mathematical transformation. And because no any method of spectral analysis could exist without the reverse transform, so we always should have a way how to go from original function to the spectrum, and also how to go from the spectrum to original functions. It is very necessary and very important, because without this, if there is no way how to come back from the spectrum to original function, so the method will not be relevant and it would not be applied for the practical task for digital signal processing. So fortunately for discrete cosine transform is this form, inverse transform exists, and the formula for it is presented here. And we can see here the two-way arrow that indicates that these two formula are connected with each other in a concrete way. So here we have a way how to find the spectrum, x capital from k, when we know original function x small from n small, and here vice versa, we know spectrum x capital, and we have a formula how to calculate x small. So this is a direct transform, direct cosine transform. It is also called DCT1, like a most common form, the first type of DCT, DCT1. So here is the direct DCT1, and here is the inverse DCT1. And also there is another form that is called DCT2, and it is also represented by its direct and inverse formulas. there are some differences between DCT1 and DCT2, how you can observe by comparing these two formulas. So here in DCT2, two boundary components of original function are separated. We have in a bracket a separate component x0 and xn minus 1. So this is the very first and the very last digit of original function that are put here as a separate component of the spectrum. And then we have a sum where the counter n is changing from 1, not from 0 like in previous case, like here, from 1 till n minus 2, not n minus 1 like in previous case, because the components with the number 0 and n minus 1 are already present here. And all other components of original function are multiplied by cosine function with this argument. Again, k, like always, is changing from 0 till n minus 1. And in order to obtain original function by the known spectrum, we can use inverse DCT of second type. And here there are a similar situation when we use first and the last spectrum component. And they are like a separate component in the calculation of original function. But anyway, this method works also, and it could be applied. So while doing spectral analysis using discrete cosine transform, you are free to select which method is more convenient or more likely for you. Anyway, if you use DCT1, then to return back to original function, you have to use the inverse DCT1. But if you use in DCT2, you also could come back using the inverse formula for DCT2. So these formulas are existing in pairs, in a corresponding pairs. And here, at least an example, because I believe that it is more simple and always more useful to understand every mathematical method and every mathematical approach by executing the concrete example. So actually there is a formulation in Ukrainian, but we will translate it right now in real time. So in data compression system, the information is firstly transformed, and then these transformed values are limited by threshold value of 0.375. So this is the first fact that we have to deal with. And just a second, I will move the formula to the proper place, like here. And then I will move, oh, not this, but this formula here. I think it's better. So we should consider to transform. The first one is discrete cosine transform that is represented by this formula. And the second one is a Walsh transform that you are already acquainted with. So you know this transform already, but here it's also the formula, it's repeated for Walsh transform. So our task is to compare these two methods in a system where there is that executes compression of the data. So firstly, we have some time series, some are discrete sequence of discrete values, and we have to transform this sequence in first case by discrete cosine transform, in second case by Walsh transform, and then to limit spectrum components of the obtained spectrum by the threshold value that is assigned in example like a 0.375. So initial sequence that is the same for both methods in order to make us available to compare one method with another one. So initial sequence is like here. It's very, very simple sequence that consists only of 4 values, 1, 2, 0, and 3. Actually, we already deal with this sequence in a part when we considered Walsh transform. So there it was an example for the same initial sequence, and we calculated the Walsh spectrum for this sequence. So now we will be able to take that results as a Walsh spectrum and then to compare it with the DCT spectrum. So we are going to find an answer for the question, what transfer is more effective for data compression? Sorry. And what is the maximum compression level in a percentage? These are very important questions, of course, not for the case when the initial sequences consist of only 4 values, because actually it doesn't make sense. But when we have quite a long original data, original signals that are to be analyzed, maybe predicted, and becomes very actual to compress the data. So that in that case, it becomes very, very important. Let's make a solution. And firstly, we will use discrete cosine transform formula in order to obtain a spectrum. So here there is a very detailed representation of the calculation. We have 4 discrete values of original function, 1, 2, 0, and 3. We could mark them like x0, x1, x2, and x3. And from previous slide, we have a formula, this one, how to calculate the spectrum. We should step by step putting the values of k equal to 0, 1, 2, and 3, because totally we will have the same number of spectrum components like it was in original function. So if we operate with initial sequence that consists of 4 values, it automatically means that the spectrum will also consist of the same number of 4 values. So our k will be consequently changing like 0, 1, 2, and 3, like it is for original function. So here is you can find a calculation, and I believe that you could understand it very clearly how it's obtained. So x capital, so the first spectrum components for the k equal to 0, we just have to put instead k here 0, and we will obtain actually cosine of 0 to 1, and we will obtain finally the value of 1.5. This is the first component of discrete cosine Fourier spectrum. Then we put k equal to 1 and obtain the next one that is equal to 0.25, x from 2 minus 1, and x from 3 0.25 again. Then we gather them together and obtain the resulting spectrum that consists of these 4 values: 1.5, 0.25, minus 1, 0.25. As you remember, in our task, it was stated that after transforming these transformed values, so it means the values of spectrum, are to be limited using the threshold of 0.375. So After we obtain this spectrum, the result, we have to apply this threshold. What does it mean? It means that if sum of spectrum components is more than the threshold, equal or more than the threshold, then we remain it like it is without any modification. But if this value is less than the threshold, so it's under the threshold, then we just make it equal to 0 because it is under the threshold. It's because of condition of this task. Because if you would have another threshold value, we will maybe have another result. But for this threshold, it should work like here. So we should compare every component of the spectrum with a threshold value 0.375. And if the model will be more than this, we will obtain the spectrum that has 2 zeros. Instead 0.25 here and here, because this value has a model less than a threshold, we should put zeros. And we obtain a resulting thresholded spectrum that consists of 2 non-zero and 2 zero components. After compression, of course, we lost the data. We have lost it because we did this thresholding. If we would not do this, our data would be not compressed. Just calculate the spectrum and that's all. But if we are talking about the compression, so it should be some informational losses. We have no way to avoid this. If you would like to obtain the less memory to storage the data, to compress the data, then we should agree that some data will be lost. And of course, there is a question how to select a threshold and what it should be and what of compression level is acceptable and so on. But here in this example, we have this result that contains 2 zero elements. Okay, then let's go to the next method, to the Walsh transform. From the previous lection, we already did this example with this initial sequence and we obtained a result like here. X from k equal to 1.5, 0, 0.5 at -1. So this is a Walsh spectrum. After we obtained it, we have to threshold it. So we have to compare each component of the spectrum with the threshold value. And a result will be like here, X from k equal to 1.5 because it's more than threshold, then 0 because it was 0, then 0.5 because it's again more than threshold by model, and then -1. So the spectrum remains the same. There is no modification, and as a sequence, there is no data compression because it coincides totally with the spectrum that was calculated itself. So it was like a situation when we didn't do a thresholding. So for this concrete example, we could make a conclusion that DCT is more effective than Walsh, but it's only in this case and only for this original sequence. If we would take another original sequence, another signal to analyze, then the result could be different, but it's needed checking for every concrete task. And my aim was just to show you how it works and what is the procedure of the calculation. And we didn't finish with this example because the second question that we were going to answer is to estimate the effectivity or effectiveness of the compression of data. And this effectiveness could be calculated using this formula. Where we have in numerator the n initial, that is a number of the non-zero elements or in initial sequence, in original function, then n transformed is the number of non-zero elements in the function after transforming, so in the spectrum, and we should divide it by n initial. Again, here is an explanation. And in order to obtain the result in percentage, efficiency in percents, we have to multiply it by 100%, of course. So comparing the two methods of discrete cosine transform and Walsh, we have to estimate efficiency for DCT as 4 minus 2. So initially we had 4 non-zero components, and after transformation 2 non-zero components, after transform and thresholding. So result is 50%. So 50%, it means 2 from the 4 values were became a 0, transformed to 0 after threshold. So the compression level is 50% or 1/2. But for Walsh, it was no compression at all, because the values after compression, non-zeros value after compression comparing with the non-zeros value before compression stays the same. So we have 4 minus 4 over 4, it's equal to 0. There is no compression. So of course, DCT is better, but only for this concrete value. Okay, so it was the necessary material that is concerned discrete cosine transform. And let's go to the next presentation that has a number 5. And it is devoted to the continuation of discrete cosine transform. So we are going to finish with this, then going to double discrete cosine transform that is more interesting, but also more complicated. And finally, we will go to compression standard JPEG. I will explain how it works and how it is connected with the method that we considered or will consider in the future. It was I promise it would be interesting for you. Okay, so when we are talking about the data compression, as in previous presentation, we could use discrete cosine transform. Not necessary only this method, but it also could be used. And one of the very important tasks connected with the compression of data is the compression of graphical images, so photographs or some pictures or drawing or what else, yeah? Because the image as usually takes a lot of volume of memory. So it is very urgent task to compress the image, because it needs a large memory volume, and of course it would be desirable to have a tool how to decrease this. For example, if we consider not so big, actually a small graphic element of the size 320 by 240 pixels, so it's quite a small picture, and with dimensions 8 bits per pixel, so it will take about 7 kilobits, and it could be compared with about 25 text pages. So it's even small image requires large memory volume. And also concerning the image, it was a couple years ago, actually quite a large time ago, it was a problem that different devices deal with the images. And as a result, they use different standards for these images. Sorry. For example, it was computers or some network devices. It could be hard disks or cameras or whatever. And till that year, 1986, it was different standards that were used in different devices. So it was difficult to realize the effective exchange of images between these devices. And that was the main reason why in this year, in the bound of organization that is responsible for the standards, it's ISO, International Standardization Organization. It was organized as special groups for the managing the issues connected with the image standardization and storing and processing. This group was called Joint Photographic Expert Group, and if you would form an acronym from this term, we will obtain JPEG, that is well-known abbreviation for the standard of image data. Okay, so it was a first and very successful, I would say, attempt to create a common standard that could be used with any device. Doesn't matter what kind of device, so it doesn't matter what hardware is inside, but the form of representation, this graphical image, would be standard. So it's more, of course, it's a more convenient. Okay. Then let's consider how it works. What is this? What is inside this standard? What is behind? So we will consider the block diagram or flow chart of the process, how the data is compressed for the image using JPEG standard. How it works, this JPEG standard. Actually, JPEG standard itself, there is a set of basic functions for the compression of graphical image. And here, this flow chart is explaining how this image is compressed step by step. So in the input, we have an image data that is, as usual, two-dimensional, like not like a text, but like an image. So image could be represented by a two-dimensional matrix, for example. And we have this data in the input. The first block, the first unit that takes the initial data is actually DCT that you already know. You know what does it mean? DCT is discrete cosine transform. So this initial data that describes the image are going to the block of discrete cosine transform. But it is not a simple cosine transform that we considered before in the previous presentation, because in that case it was one-dimensional transform, and it supposed that original data is one-dimensional data. But if we deal with image, the initial data should be two-dimensional. So this mathematical apparatus should be modified in order to be able to operate with the two-dimensional data, with the images. Anyway, as a result, of the output of this unit, we obtain the set of the DCT coefficients, like components of the DCT spectrum. We obtain this. After we obtain this coefficient, the next unit is the unit that is marked by the letter Q. It's a quantity device that is executing the quantization. And here there is the only unit and only step in data compression JPEG algorithm where we have a data losses. Like it was an example where we did a thresholding of the spectrum and some of the component becomes equal to 0. So we lost some information. And here also in the schema of JPEG data compression, we lost some information. And these losses are concentrated here in the unit of Q, quantum device. Anyway, after quantization, we have a data that is, like you can see from the flow chart, is split into the two flows of data. First one is called like a direct current coefficients. Of course, there is no any electrical current like we used to understand when we see this term current, but it means that it is like a constant component, or another name, it's a zero frequency, for example. So it's like a DPCM. This is a unit of here is the explanation of differential pulse code modulation that is applied for the only for the direct current coefficients, only for this first flow of the data. I will explain how it works in details in the following slide, in the next. But now we should just understand the whole picture, how it works. After this kind of modulation, differential pulse code modulation, there is another block that is marked like HCAC, and it is a coder. Actually, here we did a coding. It's a Huffman's coding or arithmetic order. As a result, we have a first flow of data with the compression. The second flow is so-called alternating current coefficient. So this is all other except direct current. And here, as you can see, there is the first modulation unit, like here, but there is a coding unit, HCAC, so the principle is the same. And in the output, we obtain the compressed data, compressed image that is already converted according to JPEG standard. So it's not so difficult algorithm how to compress data and how to obtain the JPEG standard image. Here there is a little bit more explanation about the steps of this algorithm. So at the beginning we have two-dimensional double cosine transform for original image. So we take original image and apply two-dimensional cosine transform or double cosine transform. And as a result, we receive density coefficient, and then we use quantization. We are applying this unit marked by Q, and this coefficient as a result are rounded or quantized. Here, I repeat that there is only one unit where we have an informational losses. Because we have a threshold, like in examples that we considered when compared density and Walsh transform. And here, then we have two, just a second. Here, then we have two flows of data. First one, this is a coefficient of zero frequency or direct current coefficients that are modified by differential pulse code modulation, like it was indicated on the previous slide on the flow chart. For the rest one, there is it's just empty, so there is no modulation step, but the next steps are the same for the direct current coefficients and for the alternating current coefficient. There is a coding using Huffman's code or arithmetic code here and here. As a result, we have two streams of compressed data that consist of coded coefficients of direct and alternating current. And also three main steps of these algorithms of compression in JPEG standard is DCT, discrete cosine transform, but don't forget that it's not usual one-dimensional, it's a double cosine transform. I will show you the formulas later. Then rounding the coefficients or quantization, so quanting unit, and then coding. Three main steps. Let's consider it. The step one is double DCT. So if we will take any image that, of course, consists of separate pixels, so we could describe the features of this image and therefore the features of each pixel of this image by such features as intensity, tone, and color. So three main basic parameters that describe the graphical image itself or every pixel of this image individually. So basic block of the JPEG standard consists, this is a square block that consists of 8 by 8 pixels. So totally 64 pixels. This is a standard block of JPEG. You should memorize this. So all the image that is to be compressed is split on this elementary JPEG block 8 by 8. And each block is converted and compressed consequently, one by one. It's important, and I will also show you later why. The principle of double DCT is because elementary blocks of image are two-dimensional 8 by 8 pixels, so we have to use this two-dimensional DCT. It means that that we can take firstly the first horizontal row of our elementary block, like here, this row, and apply discrete cosine transform like in its usual form, like in one-dimensional form that we considered in a previous presentation. So for each horizontal row separately, discrete cosine transform could be applied in an independent way. So we could execute DCT of each horizontal row of pixels. And then we have to replace each element of each horizontal row by the calculated DCT components. I mean, the components of the DCT spectrum that we obtained by applying DCT for every horizontal row. So we do DCT, we apply it for every horizontal row, and then we replace the components of this row by the obtained spectrum component. In such a way, we are able to fulfill horizontal DCT. It's still one-dimensional, but then we are going to the consideration of vertical column instead horizontal, like we did before. So after this, after we obtain the modified matrix with a dimension 8 by 8, where the values of the pixel features are replaced by the component of the horizontal DCT spectrum. After this, we take separately, individually, each vertical column and consider it like a one-dimensional original signal, and then apply the usual form of discrete cosine transforms that we are familiar with, and consider each vertical column independently, and then we should replace each of these value by the calculated spectra of vertical DCT. So this is an idea, just to consider and process firstly the horizontal row and secondly vertical row. So do at first horizontal DCT and then vertical DCT. And because if we have quite a large image, of course not 8 by 8 pixels because it's too small, but if we are dealing with some practical task and we are dealing with some real images, so we should split this image by elementary blocks 8 by 8, and the usual thing is that the blocks that are situated nearby, the neighbor blocks, have a similar characteristic. So they are not so cardinally changing so quickly. So the neighbor blocks, not always, but usually has a similar characteristic. And it becomes more simple to operate at first, just to take a small block because it's not so much calculation, and then to consider and process them step by step, one by one. And we obtain a more compression level. Okay, talking about double discrete cosine transform, we have a distribution we have to take into consideration the distribution of frequency. Because if we are doing our horizontal discrete cosine transform, so we apply discrete cosine transform for every horizontal row, then the frequency of each component is increasing from the left to the right. So the frequency, like here you can see on the picture, the frequency is increasing from the low frequency to the high frequency. And when we are doing vertical DCT, so also we could state that the frequency is increased from the top to the bottom, because we are applying consequently from the top to the bottom our vertical discrete cosine transform. It means that for the frequency we could use this dependence like logics, yeah, from low frequency in the left upper corner to the high frequency in the right down corner. As regards to the amplitude, not frequency, but amplitude, for the low frequency component, and this is like a feature, like a usual thing again, that for graphical image, the low frequency component usually have more amplitude than a high frequency. So it means that this dependence will be vice versa. For the low frequency that are situated in a left upper corner, we will have the maximum of the amplitudes. And for the high frequency, we will have a minimum amplitude. So the dependence distribution of the amplitude values will be like here. And if we use the vertical discrete cosine transform, the horizontal cosine transform for the rows and for the columns, we will obtain this distribution of the frequency. It's important because after we are going from the unit of DCT, discrete cosine transform, to the quantization unit, then it would be very important by choosing the special thresholding matrix. I will show you again a lot of promises today. Okay, so here is the mathematics, how the double DCT works. Instead one sine of sum, we have now two sums because we have to combine vertical and horizontal transforms into one formula. And so the original function that is an elementary block of JPEG standards, 8 by 8 pixel, there is a function s from y and x. So we have two coordinates because the image is two-dimensional data, yeah? So there is two values, two variables, horizontal and vertical axis, x and y, and our original function could be represented like here. And because there is two variables, so we have to multiply it by two cosine. One that will be dependent on x, and the second one with the argument dependent on y. And we have, of course, two sums. Also, we have two constant coefficients before the sum signs, and as a result, in the left part of the equation, we have a two-dimensional massive of the DCT of double DCT coefficients. It will be two-dimensional because the original function is also two-dimensional, but these two variables will be different, like in Fourier transform or in discrete cosine transform in its classical form, in one-dimensional form. We have one variable for the original function and one for the spectrum. And here we have two variables for original function for the image and two for the spectrum. But these variables are different, of course. Here we have y and x, and here v and u. So as a result, we have this matrix of DCT coefficients, like here. U is changing from 0 till 7, because totally we have 8 by 8 pixels. So the dimension of result of double DCT will be the same, 8 by 8. U and V, two variables that are changing from 0 till 7. And here is the expression for the constant coefficients, C from V and C from U, that are put in here before the sums. So they are different for different values. When V and U equal to 0, these coefficients are equal 1 over square root from 2. For all others, we and u, these values, these coefficients are equal to 1. So it's very simple. So here that is about mathematics, but as for any mathematical method, for any spectral transform, we have always be sure that we have a way and a tool how to come back, to return back to original function. So we should be sure that we have a mathematical equation for the inverse transform. If we have an initial data as a massive of DCT coefficients, so we have to know how to go from this initial data till the original function, from this S capital to the original function S small from y and x. And here you can see the proper equation for the inverse double DCT. Here in the left part of the equation, we have original data, original image, and here the spectrum, the matrix of DCT coefficients. Okay, so step 1 is finished. We have this massive, and this massive then is going to the step number 2. It's a quantization or rounding. This is only one step where we have the losses of data. What does it mean rounding? It's a process when we decrease the volume of memory that is necessary to store all this matrix. Because matrix is, has a dimension 8 by 8, so totally it consists of 64 elements. So the task of this rounding step is to decrease this value. It means that some of them should become a 0. And of course, during this process, we will have a loss of information. So for to do this, to do rounding or quantization, we have to assign another matrix that is called rounding matrix with the same dimension, 8 by 8. So we have to take from somewhere this matrix, and then each element of the DCT matrix that we obtained from the previous state, we have to divide by the corresponding element of the rounding matrix. So in the initial, we have DCT matrix, dimension 8 by 8. Then we divide each element by the corresponding elements of the rounding matrix, 8 by 8. And then we are doing rounding to the nearest integer number. And here is the step when we obtain some zeros instead non-zeros component. And these values of non-zero elements will be minimal in the left upper corner. Why? Because from the previous slide number 8, we saw that the amplitude is maximum for the left upper corner. So after dividing by whatever and then rounding to the nearest integer, we will obtain the less probability of 0 obtaining. But for the lower left lower corner, we will obtain the more probability. So the values of zeros element will be maximum here and minimum here. And also the round matrix should be constructed in the with consideration of this logic. So the values of rounding matrix should be minimum in the left upper corner and maximum in the right down corner. In such a way, during the choice of rounding matrix, there is a different question. From one side, it is necessary to provide a sufficient compression level to make a compression more effective. And from other side, we have to still to have enough quality of image after compression, because in other way we could obtain the compressed, very well compressed image, but the quality of the image will be terrible. So there is like balancing, like a compromise that should be found, and the solution lies in the choice of rounding matrix. Actually, the standard JPEG doesn't recommend any kind of rounding matrix, so it could be chosen different. but it could be chosen taking into consideration this balance. And actually, ISO, Standardization Association, developed some certain recommended set of this rounding matrix. And the rule of the forming of this matrix actually is very simple algorithm. At first, we should select one number in the interval from 1 till 25. This number is called quality factor, or shortly QF. And this value, this parameter defines the step how the values of in-rounding matrix will be increased when we are looking to the main diagonal of this matrix. For example, quality factor should lay in an interval from 1 to 25. Let's select it equal to 2, like here. All elements of the matrix are calculated using this formula where we have this quality factor like UF. So each element that has the coordinates y and j, so y is a horizontal coordinate and j is a vertical coordinate, is calculated like 1 plus, and then we open the brackets, 1 plus I plus j, close the bracket and multiply by q. So changing the QF, we will obtain the different step between the next values of elements of rounding matrix. If we take QF equal to 2, then we could obtain this form of matrix. You could check it. For example, for this left upper corner, we have I equal to 0 and j also equal to 0. So we could put 0 here instead I and instead j, and we obtain 1 plus 0 plus 0 multiplied by 2. So 1 plus 2 is equal to 3. And so on, changing I from 0 till 7, j changing from 0 till 7, you can calculate it very simply. For example, the last element where j and I are equal to 7, we could obtain 31, like putting 7 and 7 here instead of y and j. So as a result, we have the ready rounded matrix, and then we should apply it. So we should take the massive of our density coefficient and consequently divide each element of this massive by the corresponding element of the rounded matrix. And for example, if we have this form of matrix for this quality factor, let's have a look to the last element that is that is equal to 31. And the consideration is that if we have a corresponding element in a matrix of density coefficient that we have to divide by this 31, so this value should not be less than 16 to be non-zero after rounding. If not, if it will be less than 16, then after rounding, we will obtain zeros. So rounding is only one step, as I told you already a couple of times, where we have informational losses. After this, we have an amount of zeros that will be minimum to the left upper corner and maximum to the right down corner. And because most of graphical images are containing low frequency information, so the share of low frequency information is much more than a high frequency, that's why the amplitudes will be maximum for the low frequency, and that's why it will be less zero elements after rounding in the resulting matrix. And high frequency component of the matrix could be easily deleted. Actually, there is their impact on the quality after compression, it's much smaller than for low frequency components. So it's more important to save and to keep low frequency components than high frequency components. And this is actually the idea of the data compression using JPEG. And as a result, we have a compression by more than 90%. So the data is compressed dramatically. Okay, and the last step is step number 3. It's modulation and coding. After rounding, we are going to the splitting the data flow into 2 flows, direct current coefficients and alternating current coefficients, as you remember from the flow chart on one of the first slides of this presentation. So this is a final step of JPEG compression algorithm, and it implies 3 operations on resulting matrix. First one is discrete pulse modulation, then coding of repetitions, RLE coding, and also entropy coding or coding Huffman. And how these methods are working. So first one is replacement by relative values. This is a modulation that is applied only for the coefficients of direct current. And actually, among the 64 elements in a matrix with dimension 8 by 8, only one value is called the coefficient of direct current. This is a value with the coordinate 0, 0. So here there is only one of 64 coefficients is direct current. All other 63 are the alternative current coefficient. So only for this one element with the coordinate 0, 0, we are doing and we are applying this modulation DPKF. Actually, what we are doing, we replace the absolute value by a relative value. So for this, we have to take not only this matrix that we obtained on the previous step, but also the same matrix, but for the previous block of 8 by 8 pixels, because in the beginning I told you that all the image could be divided by elementary block. Each of this block has a dimension 8 by 8. So here we have to compare the 2 nearby blocks with each other. Actually, not all the blocks, but only one element from each block, this element 0 by 0. And here we have to find a difference between the 0, 0 element from our current block with the 0, 0 element of the previous block and replace this absolute value by the difference. That's why I told you before that it is very important and useful feature that the nearby placed blocks are similar for the image. Usually they are similar, so it is more convenient to use not absolute values, but the difference between this, because the difference is not so large. So no need to use a large volume of memory to keep this value of difference. It's easier and it's more convenient to store the difference instead the absolute values. That's why this difference modulation is applied for only one block with the coordinate 0, 0. Okay, so we do it like here. Here is the equation, how we calculate the 0 and how we replace it. All other 63 coefficients that are called coefficients of alternative currents, here there are, they are using by bypassing of matrix element, starting from here, and here you can see the route, how these elements are considered step by step, one by one, from the 0.1 coordinate 0, 1 till the last one with the coordinate 7, 7. So here is the pathway how to process them consequently. And during this path, there is using a coding, and these coding are used on the base of the algorithm of rank length encoding, one of the most old and the simple archiving algorithm. So now we are dealing with the archivation. It's a compression. So we replace the chains of symbols that contain the same bits by the pairs. when we have first number that indicates the counter and second the value. For example, if we have 16 based counting system, so we have some bits that are equal to A, B, C, and so on, and we have a repetition of the same bits. For example, here we have 3 times bits equal to D, and so we can replace this by 3D, where 3 is a counter and D is a value. And of course, the more repetition we will have, the more positions we will save, and the more level of compression we will obtain. So this is a very simple idea that is used here in the algorithm. And then also there is a entropy coding or Huffman's algorithm that is very simplified scheme of Huffman coding that gives a result in the form of following triple change. First one is number of zeros, how many zeros we have before some repetition of non-zero element, then number of non-zero element that are repeating, and then the value of this element. So it's like a previous one, but also with additional consideration of zero element. So number of zeros, it's amount of repeated zeros before the current non-zero element. Number of elements, amount of bits that are placed next, and then the value. And here on the last slide in this presentation, you can see the correspondence between the number of elements and the value of this element. It's very easy. For example, if we have a number that lies in an interval from -1 till 1, so only 1 bit is enough to code this. If we have more range, then more bits it's needed, so it's not something unique. Actually, there is a way how the JPEG standard is functioning for the image compression. And I hope that my explanation were helpful for you. After this, if you will have some question, we will discuss it during our meeting. If not, I will place the practical task devoted to the discrete cosine transform into Google Classroom, and you will be able to do it, to execute it. Okay, thank you very much for the attention, and I wish you all the best. Bye.